Hello.
Sure.
Hello. Yeah.
Sure.
Yeah. So you can hear me, right?
Yes, sir.
Okay. So let me share my screen, and in the meantime, you guys can tell me. Yeah. Yeah. So do you have any questions, doubts regarding whatever has been done so far? Hello. No doubts, no questions. Did you guys actually think about some of the questions or not? Think of whatever you did in the last class?
Yes, sir.
Yeah. Okay. So you don't have any questions, right? Okay.
No,
So perfect. So let me then straight away jump into whatever we are going to talk about today. Okay. So let's see, where are we now? Okay. So as I kind of told you, so maybe I can start writing one by one. So what all things have you seen? We have seen this something called a selection sort, insertion sort, bubble sort, merge sort. Then we had the quick sort and the randomized quick sort. And for each of them, we were kind of looking at we were keeping a tab on certain number of things. Namely, we were looking at the worst case runtime. We will also look at the average case runtime. Or maybe even the average case runtime. Then we also have this space complexity, right? Amount of space required. Now there are some other stuff that we have looked at, but let's quickly for this lecture, let's think of just these three things for now. Can you hear me properly?
Yes, sir.
Yeah. Okay. So the selection sort was order n squared. This was also order n squared. This was order 1. Insertion sort was also order n squared. We were basically not making any progress in this respect, right? But then in the merge sort, we certainly made a lot of progress, and it became order n log n, and this became order n. And in the quick sort, this unfortunately went up bad, but at least we managed to get this average case quick sort, this one, and the space became constant. Wow. So this is where we are. Okay, let me not worry about the randomized part. The randomized part is, of course, this will not be in this record, but this is a randomized algorithm, right? So maybe I should just delete this thing. We did this randomized thing kind of to talk about this average case runtime. Now, of course, there were a couple of questions that was given to you guys. Did you guys manage to, or how many of you managed to prove that quicksort or randomized quicksort algorithm not only is in n log n expected runtime, but with almost high probability is in n log n? Did anybody get it?
I couldn't do it, sir.
You could not do it. What about the rest? Okay, now I think this is getting me under my skin. I have to start asking people one by one. Chandramouli Chakravarti?
Yes, sir.
Yeah. So if you have not done it also, can you unmute and say that you have not done it or could not do it or something? Okay. You could do it, Chandramouli?
Yes, sir.
You could do it. Arey bhai, Chandramouli, are you talking? Can you keep yourself unmuted and for 2 seconds? Yeah, I can hear you, Chandramouli, but you're keep making yourself muted again and again.
Hello.
Yeah, I can hear you.
Yes, sir. Yes, sir. Yes, sir.
Yeah, so could you do it?
Sir, can you repeat?
Okay. So could you prove that this quick sort algorithm is almost always n log n?
Is that the average one?
Average one I did in the class, right?
Yes, sir. Yes, sir.
But then we also gave an exercise to kind of try to prove that almost always with probability 1 minus model of 1 runtime is n.
Sorry, sir. I couldn't do that. No, sir.
Okay, so Chandramouli, I mean, this is something, I mean, it's fine that you have not done it, okay, so that's not a problem. But what I'm getting very irritated is the fact that it seems that you are not even listening to what I was saying now, right?
So actually, there was a dog barking.
Whether the dog bark or not, I mean, listen, this is the first time I'm hearing your voice itself. And I mean, can please someone tell me that how many of you are actually interested in this thing, in this course? So this will be, I mean, something help me a lot. If you're not interested at all, then I suggest that you don't come to the class. That's perfectly fine. I mean, this is something I hardly hear any one of you say anything. Okay. Let's say Zaira Haram, are you there? Zaira Haram, are you there? Okay, I think you have entered and left. Excellent. Yakshit, are you there?
Zaira is using the chat.
Huh? Sorry?
Yes, sir.
Okay. Zaira, you sent something. Okay. So did you okay. So okay, why don't all of you write at least something in chat? I want to hear something. That could you do it? Or have you tried it? Just answer two things. Okay. I could not do it or I didn't try it. Can you just send everybody, can you send a chat message? Okay, I get the idea. The interesting part is that there are 25 participants in this class right now. 16 of you have replied. So the other 9 of you are kind of basically you're giving your attendance. Okay. I mean, yeah, I mean, what can I say? I mean, if you are not interested in this course in the third week also, then you are just not interested in this course. And I mean, nothing much that I can do about it. And even my whole attempts will be completely useless to convince you to kind of put focus on this course. Yeah. Okay, but as I told you, I mean, I am putting these videos online, and I am going to take it down without doubt. Every video that I upload, I will take it down within 1 to 10 days. Sorry, 7 to 10 days. 1 week to 7. And then it's up to you to figure out what to do and what not. Okay, so let's go ahead. So, okay, so we had this quick sort. Now, question that we had managed to prove at some point of time, not remember the last time, which all of you understood, is that the number of comparisons for any algorithm, not just the above algorithm, but any algorithm that one can imagine or do, the worst case runtime, in the worst case, has to be bigger than n log n. So any algorithm which is a comparison-based algorithm, so they are comparing and then deciding, so they have to be n log n. Okay, so in some sense we are very close. So merge sort of kind of achieves the best you can think of, except that the merge sort has space order n. And now, of course, the next question would be, can you produce something of this form which has the worst case n log n? So even though, of course, the average case will also be n log n, and the space is order 1. Now, this is a question that can you produce such an algorithm? Now, so this will be the, so in this class, we will see one such algorithm. And this is possibly one of the very few classes where we will be going into a little bit of data structures. Okay. So now let's see. So,
Sir,
yeah, go ahead.
sir, I just wanted to ask, this big omega sign is like a greater than equal to sign.
It's a greater than equal to sign, yeah.
Right. Is there a sign for strictly greater than?
Yes, this is the small omega.
Okay.
If I had told you this one, that means it will be, I mean, strictly bigger than, meaning it's a quantity that is way much bigger than this, meaning that
Right.
n log n by that quantity goes to 0.
Right. Right. So n log n is small o of the other quantity.
Right. Yeah.
Right.
Okay. But here it is not omega, small omega. Here it is just bigger than or equal to. Okay,
Right.
it's big omega. Because of course we know that, see, we have already got a algorithm which has order n log n, right?
Right.
So we cannot expect to have anything big, higher. The lower bound cannot be higher than n log n in any case. Okay. So let's see. So to understand this kind of the algorithm that we're talking about, let us go back to the selection sort to some level. Sorry, not selection, the insertion sort. You guys remember the insertion sort? So what was the main idea there? It's like, okay, fine. I have a, so maybe I will do it in a slightly different way. I mean, that is not exactly how the insertion sort has been done for you guys. But basically you have this array A. I mean, let's not worry about the space for now on, okay? Just for now, just forget the space. And this is some kind of, all values are there. And what we do is that we kind of, maybe we can create a completely empty space to begin with. And when the first element comes, say, which is say x1, I put it here. When the second element comes, I compare with x1. So this is my, at that point, okay, we compare with x1, and then we either, if it is less than x1, then I'll put x2 over here and move x1 over here, and so on. And basically, after we have, say, looked at the first k points, k1 to ak, we have put this whole thing out in this set in such a way that this is ordered. Okay, so maybe I have got it into the form xk, then x3, then x1, then maybe x5 or something like that, but which are all basically in the sorted order. And now when I take this next element 1, I will take this one and go and try to find out where I can place this thing. Right?
Yes.
So which place should I place it? And I will do that. I will place it there and move this whole chunk a little bit further so that the whole the updated list here. So if this is the A list, this is the B list. The B list also remains sorted. Right. So in high level, what are we doing? So the B is basically a way of storing the values of or any values such that the B is maintaining some structure. What is the structure it is maintaining? It is maintaining the structure that in B, every element is placed in a sorted way. So B is kind of what we can call as a data structure to some level. Okay. And what is the data structure? It is kind of storing the data in a structured way. Okay. In this particular setting, B is a data structure which is a sorted, say, array. Okay. Good. And okay, so B is a data structure that is a sorted array. And the algorithm basically uses 3 or 2 operations rather than, so say something like that. One is that if I have a particular B, I have to, or maybe forget the particular B, I have to just do insertion of an element in B. So I have a new element comes in, which is the next element in this rounding. I take that X and I want to insert this object into this current B, such that I want to insert it such that, of course, the updated array is still the same sort of data structure, meaning it still is a sorted array. Right? And if we can do that, then we can repeat it one by one. Is this clear? That this is what we are doing in the case of insertion sort. Yeah, somebody was saying something?
Sir, you already have an array A of some elements of n elements.
Yes, they are not sorted.
They are not sorted, and you have created this structure B with some property.
Yes, I want to maintain, I want to store data here such that some property is being maintained.
Sir, but how did we save on space then?
No, I'm not saving space. I'm not talking about space right now. I will come to that later on.
Okay.
Okay. So actually, if you think of it, what is being done in the case of insertion algorithm, okay, is that at any point of time, what happens is that there is a, so this much algorithm is basically a sorted list and the rest of them have not been looked into. Right. So in some sense here, we are kind of maintaining, so this first, some part of it, whatever data has been processed, so that is a sorted array. So in some sense, B is being stored along with A in the same space. Is this clear?
in a sense,
repeat it again.
So in a sense, this insert function,
Yeah,
is a member function of the whole construction of B, right?
right, right.
Because B itself is characterized by the fact that it is always sorted.
Yes, B is something that always maintains sorted. So that is something. I mean, in the original insertion algorithm, it was the first half, right?
Right.
And whenever I'm taking a new element here, X, I have to insert in B. Right? I insert in B, what it basically I find out a place and then somehow insert it and move it, and then I move this. So basically, the B size of B slightly becomes bigger and comes here.
So B is a dynamic array then.
It's a, you can say dynamic array. Okay.
Right.
I mean here because the arrays is already A, but B is basically a data, is kind of a, the main idea is that B is storing a particular, storing the data in a particular form.
Right.
Okay, so that is basically what B is doing. I mean, we are managing to do it in the same space without making use of any new space. But that's a separate issue. But the main idea is that we are having this B, where the B is a kind of a data structure where we can insert while maintaining the structure of.
So in the C language, we had learned the concept of, or maybe not in C, but in C++, there's this concept of a structure data, the data
Right,
structure.
that is a
structure.
different kind of structure, right? That you kind of store is like a, it's like a set of data, that set of information that you store in one particular place.
Right, and then you have private and public accessibilities.
Yeah.
So in this case, the data structure itself will be private, because if it was public, then we could just manipulate it however we wanted. But then it has a member function, which is this insertion, which will ensure that it will always be sorted. So we can.
Yeah, you
call
can think of it
public.
like that. Yeah.
Right.
Right. Although, I mean, see the data, the structure concept is slightly different. It's like a kind of what you are kind of stored as a big, I mean, what do you mean by a big alphabet kind of stuff like that? Kind of, I mean, how you have to store, what all information are you storing in one cell? That's kind of what the in the C++ the structure kind of talks about. So that's the kind of data structure. Okay. But here it is slightly, yeah, I mean, there are lots of different kind of data structures. So storing data in a structured way is data structure. Okay, data structure is no new weird objects. It's like a nice, beautiful way of storing data such that we can do certain operations on those data while maintaining the structure. Okay. So maybe you'll have a slightly better understanding when I talk about the structure, the data structure that we're talking about here. So let me say that this is what I will be targeting for. Okay.
So it's like the data structure is, it's like you're defining the whole fabric of this structure, which is not just the memory itself, but implicitly there are some conditions that you've imposed on this.
Right.
So
Exactly.
whenever you seed a change anywhere, then the whole change has to be reflected with respect to that,
right.
with respect to that condition that you imposed.
Exactly.
Right.
Exactly. Right. Okay. So say, what happens if I want to store? Okay. So okay. So this is what I will do. Okay. I want to design a data structure. Now, what does this mean? Meaning, I mean, store data in a structured way, whatever that means. Okay. Such that, okay, I am allowed to do the following. Number one, I can insert an object. Insert an object. If a new element comes, I can say, oh, now store it in the data structure in that set. And how will you do it? I can, okay, remove an object. Okay. So I can just say, oh, okay, come, this is the case. No problem. Just remove one object and this is an object, please remove it from there. So of course, while we do the removing, I still want to maintain this thing. Okay. And the third thing is that, say, I can ask, there are a lot of different things. So every data structure is designed to satisfy certain number of this kind of black box access you can think of. Okay. And we can say that, okay, the other thing that we can say is that, okay, can you give me the minimum? Meaning among the set of data that you have stored, give me the minimum among them. You have to give me the minimum.
Sir, hello.
Yeah.
Sir, determining the minimum of a data structure, is that a property of the data structure, or we
very
need
well
to
be a property of data structure.
Sir, like you are talking about like tree, like suppose left side is greater than the middle and right side is less
Right.
than.
Say
In
whatever.
that,
Yeah.
okay.
So that's a data structure, right? So we
Yes.
kind of right.
And so another thing, insert an object X and remove an object X from anywhere from the data set.
Right? Sorry. Yeah.
Sir,
Anywhere from any
anywhere.
element. Okay. Any element. Right? Yeah. Yeah. Right. So now, okay, so these are kind of when we design a data structures, there are various data structures that are there, where the main idea is that you store a data and I'm only giving you a limited access to the data and say, okay, these are the only questions that I want to answer. I don't want to give me directly what is the median of this data of this set of objects. No, I'm not asking that. I'm not going to ask that at all. I'm only going to ask you these three things. Then, can you design a data structure which minimizes the amount of cost taken to perform this object?
So could you please repeat the question?
So I have told you that, okay, somehow store your data. Okay. So let's think of it this way. Okay. You have the set of books, right? In your library, there are you have a huge collection of books. You can store the books in various ways you want, right? You can store them according to subjects. You can store them ordered according to the author's name. You can store them according to maybe the publication's name, and so on and so forth. Now, why or how do you store it, say, or how does in a library things are stored? If you see this library, these things are not stored in terms of alphabetically.
Yeah, they are categorically sorted.
Yeah, sorry.
They are categorically sorted.
They are first categorically, right?
Yes. Sir.
First, they're categorized based on subjects, and once they are categorized based on subjects, under that they store it in terms of the in this alphabet, in the alphabetical order. Now, why is it so? Why do you think is it so? Right.
Sir, so that we can easily access the book. Suppose if you want the book that is the cover statistics, then we don't need to move to mathematics section for looking.
Right. So idea is that most of the time that when you want to, how do you want to access the library, right? You want to access the library by saying that, okay, I want to find this book which is on mathematics written by, say, Rudy. So go to mathematics section and then search out Rudy. All right. Now imagine if the data was stored in an alphabetically in terms of the R, in the author's name. Total. Right? Then will it be easier for you or not?
So,
Sir,
Yeah.
if I am searching for a certain author's name, then it will be easy. But if I am searching for a subject, then it will be difficult.
Even that is not easy. Okay, I will tell you why. Okay, so R is somewhere. It's a huge collection. Maybe think of this ISI library, right? 3-story building. a 3-story library kind of stuff like that. And you're looking for a particular R, author's name, right? Then you have to find out where that R is. Where is the starting and ending of the R, authors are, and all the authors' books starting with R, right?
Yes, sir.
Basically, you do a binary search on that, right? That's the best you can hope for. So it will be log of number of times you have to look and find out. Oh, this is okay, this is S. So this must be on the right, left of it. Oh, this is P. That means it is on the right of it, and so on, right? Number of queries that you will need is log of the whole thing. Log of the total number of books in the
So
library.
this is so this is because we have more number of authors than type of subjects, number of subjects.
That is because we have, but that is, yeah, even yeah, I mean, the total number of books, right? All the authors are there, right? Now, when you are talking about types of subject, right? You have given me some extra information. So if the library is only sorted, kept every book in terms in sorted in author's name, and you tell me that see, this is a mathematics book. Now that information that is a mathematics book is completely useless for me. So that will not help me to search it, right? So there might be a book by some other routine on physics also. Okay, or some other book on literature also. So it doesn't matter for me. So total searching can be done in just log of the n, where n is the total number of books, right? So basically, what I mean is that if the library sorted the books according to authors, then finding a book would take order log n, where n is the number of books in the library. Right.
So in a sense, the more number of classifications we can make, the easier to be to find.
Not exactly. It's a kind of a trade-off there. So this is a very interesting thing. Okay. So let's think of it. Okay. Now, so let's look at it. That what happens if it's the case of others. Okay. If the library sorts. Okay. First of all, it's kind of sorts according to subjects, and then sorts according to authors. What happens there? So you're looking for this mathematics book of routine. How much time will it take? First of all, it will take, again, same thing, right? You have to first of all go and find out which shelf or which rack contains the mathematics book, right? Or mathematics book, maybe analysis book or something like that, right? So it will log of S, where S is the number of subjects. But then what?
Then order of log of the number of books in those.
It's the number of books in this subject.
Yes, sir.
Right? And this value, S times NS, might be for many subjects very low, very less. So basic idea is that if you are looking for, say, I don't know, a book on linear algebra, and linear algebra is a subject, and there is some 1 million books on linear algebra, your life doesn't make any better. It's pretty hard job. But if you're looking at a book on, say, measure theory, and there are only very few books on measure theory, then of course, this one you will go and find out where the measure theory book is, and the rest of it you can do it in very quickly. Right? And the main idea is that, yeah, sorry.
The last expression should be added, not.
Yes,
I
sir.
just
It should be added. Sorry, added that. Yeah. But added basically means that this will be equals to order of log s times ns. Right. So that's what I meant. Correct?
Yes, sir.
Yes, sir.
So for many subjects, s times ns can be low. We kind of say that, okay, see, I want to order my books in such a way that if a person is coming and looking for a book in a subject which is not that big, okay, then they can find it out easily. But if not, then it becomes a complicated. Okay. There can be other things also. Say, I want to answer. Maybe the library wants to answer questions like, how many books on group theory are there? This is something that the library always wants to ask some kind of question. So, okay, group theory is an important subject. It is required by a lot of students. And maybe I don't have to keep the same book multiple copies, but as long as I have enough books on group theory in general, then students will be able to read it. So I want to store a certain number of books in group theory. So at any point of time, I want to know how many books in group theory are there. Right? Now this question, as you can possibly understand, can be easily answered if it is stored in this way. But if it is stored in sorted according to authors, then this is not at all easy. Right? So in some sense, all I'm saying is that the library stores the book in such a way that some standard questions can be easily answered. Okay. This is the main idea. I was, okay, what happens if somebody, I go and ask how many books has maybe, I don't know, how many books has, say, Gauss has written. Okay, now there can be, Gauss might have written books in various subjects in mathematics. He might have written various subjects in physics. We have written various subjects in engineering also, God knows. And so it's completely complicated to go and count it. But the question is that, is the library expecting to see questions like this? Or questions like, how many books Gauss has written?
No, sir.
Yeah, so if so, library kind of tries to understand what all questions are going to be asked and accordingly stores them. Okay, so this is how any storage system happens. Okay.
So
Yeah.
if we have more number of classifications,
Yeah.
then the only way we can find the trade-off that you were mentioning, the cons of that could be when somebody knows that they want a book by Rudin, let's say, and all they know is that it's a book in mathematics.
Yes.
but they don't know whether it's in group theory or analysis or
Yeah,
another
right. That's the
subject.
problem.
So then they'll have to go through every single
Right.
classification.
Yeah. If they don't know that information, that's not good. So that is also the reason why you should not have. So exactly. So it's all about. So this is in some sense you can think of. I mean, the storage of books has to be done in such a way that the library users are helped. Right? They can access the book whatever they're looking for quickly. And for that, you have to kind of library has to know what kind of questions are being asked. Or can the person, so if the library thinks that chances are very highly that people will just say, oh, I want a book of routine in mathematics, and not knowing exactly whether he's looking for a book of routine in analysis or book of routine in algebra, he will have to spend more time. But maybe the library thinks that no, if somebody knows what kind of book he's looking for, he knows that much of subject. That okay, he's looking in algebra or analysis. And now, I mean, you can say, okay, in analysis, so are you talking about real analysis or complex analysis? That's again comes down to the point. What does the library believes? Kind of the questions, knowledge that a user might have. Right?
Yes. Sir.
So basically, it's all about the art of storage is all about you first identify. Okay, you first identify the questions that are questions or that will be asked or that has to be answered. Okay, and then store data to optimize the time for answering the questions. For answering the questions. Okay, so this is always the case of data structures or storing data. Okay, you must see the same thing in your statistics also. Whenever you do kind of a computational part kind of stuff like that. Okay, how is the data given? Okay, you will have lots and lots of data. You can store the data in 1,000 different ways, right? But you want to store it in such a way that you can quickly say what you want to answer. Okay, and now this art of producing a way of storing this data, this is the subject of data structure. The data structure is basically the art of storing the data that answers some questions optimally. That doesn't mean that it cannot answer other questions. It possibly can answer other questions also, but that might take a lot of time. The data storage has not been optimized for this purpose.
Sir, the
Yeah.
whole file system in a computer is a data structure itself, right?
Yes. Everything is a data structure. Everything is stored in a data structure. Every possible thing is stored in a data structure. Now, all you have to understand is that these data structures, so various data structures have been designed which kind of answers different kind of questions. There are some standard data structures. Okay. So let me give you today what we will do. I will describe you the data structures of heap. Okay, and the main idea here is that it will be answering the three things. Okay, it is storing data. As I told you, it will say that at any point of time I can insert an element X. So I can give you a heap. Okay, so an heap 8. I can give an heap 8. I can insert an X in the 8. What does it mean? I can add that X in the 8. Of course, the data structure will store now one extra data, right? But however I store it is still a heap. So I maintain heap structure. Okay, I can delete an X from the heap, and I can, okay, I can ask, or whatever, I can find the minimum in this heap. And the best part will be that I will be able to do this one in order log n. Now n meaning, so n is the, say, the size of the heap. Okay, n equals to size of the current heap. I can do this one also in log n, and I can do this one in order 1. Okay, note that this is something that, say, sorted list cannot do. If I say that, oh, here is a sorted list, put this element inside, then insert will take order n in the worst case. Delete will take order n. Yeah, minimum can be done in order 1. Right? By the same time, what a sorted list can do is that I can tell you that what is the median. A sorted list can output the median in order 1 step. Here I'm not saying anything. And in fact, I will not be able to do it. Okay, it will take order n to do the median. So it's a trade-off. Sorted list can answer certain questions very quickly, and the other questions not so quickly. Here also it will answer some questions very quickly, and some other questions it will take some time. Okay. Okay.
So,
So
in a sorted list, you mean like a linked list, or
doesn't
an
matter
array?
whichever. You can think of it as linked. Yeah, think of it as the array. Yeah, in a linked list, finding the median is slightly harder.
So then, in that case, if you're saying that the list is already sorted and we want to insert it in such a way that it remains sorted, right?
Yeah.
So doesn't this algorithm where we look at the middle element and we compare it with X,
right?
And if X is bigger, then we look at the
right.
array from
Correct.
What the array which is or the upper half of the array,
Right.
and we use a recursion on that.
Yes.
So wouldn't that algorithm give us an order log n?
Think about it. Think about it.
Shifting also might be.
Right. So if I want to insert 3, right?
Right.
In log n step, you will know that, oh, this is where 3 has to insert it.
Okay.
But I have to move this whole object. I have to make space for that.
Right.
Right.
Yeah.
And
And
if it's an array, then I will not be able to. I have to do it. I have to take n step.
Okay. And in the case of if we were to use,
if it's a linked list, then I cannot do binary search.
Right.
Right. So in sorted list, either in the list in the array format or the this format, what is that called? In the yeah, so maybe this is something that's good. So in the, if it is an array, right, sorted array, then insertion will be how much? Insertion will still be order n, right? Deletion will also be order n.
Right, because of this shifting step.
Right. But if it is a sorted number stored in a linked list, right, then insertion will still be order n. But deletion, that can be done in order 1.
So, but we need to locate that element.
No, I'm not locating. I'm just telling you. Okay, so maybe. Oh, okay, go and delete that particular.
So, but then X is the element that we want to delete. It's not a
yeah.
vector.
So you can think of it X, but you can think of right. If you're just given an X, then then that will take order n.
Because linked list, any searching algorithm in a linked list is order n.
Right. But if you are kind of pointed out that, okay, here is the X, that is where it is located, remove that. That can be done here. Right. So there are positives, negatives in both of this.
Yes.
Okay. Okay, so let me just do it in this. Let me tell you the heap thing, and that's like I think this will become more clear. First of all, I'll describe the heap. So, what is a heap? Let's see. Heap is nothing but a binary tree. Okay. Now, it is not only binary tree; it's a balanced binary tree. You know what is a balanced binary tree?
Yes, sir.
So, like binary trees are like we start with the root, right? And there are every point has two things, child, at most two things, right? And maybe this can be a binary tree, right? Every point has two child. Since it is, I have a root, kind of, I kind of know that, oh, so this, so it's like the parent kind of stuff. So every node has exactly one parent, and every node has at most two child, either a left child or a right child. So that's a binary tree. But this is not balanced. Why not? Because see, there is like this node. Okay, I could have so like this one has only one. Sorry, so this child has only one node. Okay, and so on. So that's a big problem. So I want a balanced tree is basically you look at this whole tree. Okay, now look at the ones at a maximum depth. Okay, if you look at the ones with just above depth, this is complete. It's a complete tree. Okay, and if you look at the last set of leaves, the leaves at the highest depth, then they are filled from the leftmost to right. So this is not. This one is not a balanced tree. Okay. So is this definition of balanced binary tree clear?
Could you please repeat once again?
Yeah. So balanced binary tree is what? Okay. So see, you can see that there is an ordering, right? There's an ordering from each layer. For each layer, I can an ordering from the left to right. Right? So I can give you the formal definition, but yeah. So basically, let me give you the informal definition first. Okay. So let the depth of the tree be D. Okay. This depth is D. Okay. Then the tree up to depth D minus 1 must be complete. What does complete mean? They just take this one.
And it cannot have more leaves.
It cannot have more leaves. Okay. It cannot have more leaves, it cannot have more child. It's complete. Okay. And not only that, in the last row, in the last depth, okay, the leaves are filled from left to right. The leaves.
Sir, so in this diagram that you have drawn,
Yes.
so in this case, if we delete the rightmost leaf, so will that be a
Yes, that will still be.
okay, sir.
If I delete the last one, this is still fine.
Okay, sir. Okay, sir. I understand it. Thank you.
Okay.
Yeah.
So, but if we were to introduce that right child again and delete the left child of.
Sorry.
So if you were to introduce the right child again and delete the left child, that won't be.
That is not be a. Yeah, if I just delete this one, sorry. This is
okay.
not.
So the left and right have.
Yeah. There's the ordering. Left is
okay.
left of right. Okay. There's a very strict ordering.
Okay.
Okay. This has some nice advantages. I will tell you why. Okay, but let's see first. Is this kind of understood? The definition?
Yes, sir.
Of course, the formal definition you can see from the book or you can find it out yourself. But this is the informal definition. My job is to make you understand what is going on here. Okay. Now let's start numbering this. Okay. So this is 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's standard numbering from left to right and top to bottom. Right? Now suddenly I tell you, okay, can you give me the what is the left child of 5? What is the number of left child of 5? Can you tell me?
Sir, what is what?
What is the number of the left child of 5?
10.
You can
Sir,
say 10 by looking at it, right?
Yes.
What is the child? What is the number of the left child of, say, a right child of 3?
7.
7. You're saying it by looking at it, right? Now I am
Right.
saying it this following thing. Okay, it's an observation. The left child of the node I is twice I, and the right child of the node I is twice I plus 1. You can try to prove it yourself. If I draw
We
this
can prove by
complete,
induction, right?
can use induction also. Yeah, there are various ways of proving.
So it's interesting to note, like if we were to number them in a binary system,
Yes.
that could also be a way to show.
Okay, I think I know what you're talking about, but I'll come to that. Okay. Maybe I will just give you guys just a couple of minutes to think about how to prove this particular observation. Okay, so I've taken the hit. Okay, think about it. What's the definition of hit? And I have put them, I've numbered them in this way. Okay, then what is the, then I can talk about the left and right side here like this. This step. Okay, so I'm giving you a couple of minutes and I'm asking you to prove the observation. Yeah, so why don't you try to do it? A couple of minutes.
Sir, can you just scroll up a little bit?
This one.
Yes, sir. Yes, it's fine.
So maybe I can write it down here. Okay. So if maybe this will help you observe, this is observation. Okay. If it is I, then its left child has to be twice I, and right child has to be twice I plus
Yes, sir.
So did you guys get it?
Yes, sir.
Yeah, you can do it by very various ways. I'm not going to do it right now, but yeah, one induction is a very simple way you can do it. And there are other ways of kind of seeing this structure of a tree and so on. You can do that also.
Yes, we can just use the depth and say that the
Yeah.
ith element is between 2 to the power d minus 1 and
Correct.
2 to the
Yeah.
power d, then
Exactly.
just use that.
Yeah, you can do that also. But what happens here? Okay. So what happens here is that if I tell you just in the opposite, if I tell you that okay, here is a node, consider node I. You can answer, you can just say what is the parent of I. This is very easy to do, right? It is I by 2. Left child of I is of course 2i psi, and right child of I is 2i I plus 1. So in some sense, I don't have to store any non-trivial, what to say, pointers and so on. So if I have this tree, okay, so now let me just write here instead of doing it. Maybe we could use green say. So if I'm storing data over here, okay, so maybe I should write, sorry. Say I want to store data. I want to store some data over here, okay, in a complete binary tree kind of stuff like that. And I'm storing what? Here I'm storing x1, here I'm saying x2, or maybe I forget, I'm not saying doing this x. I'm storing the data A, data B, data C, data E, data D, data F. Right? This is same as, identically same as storing it in an array. How? By numbering this stuff accordingly and then writing it. A in the first place, B in the second place, D in the third place, C in the fourth place, E in the fifth place, F in the sixth place. Do you see that basically this heap structure is basically storing it in an array. Now you said, oh, okay, so this, what happened to this E? What is the parent of E? Okay, let's see. What is the parent of E? The E's coordinate is 1, 2, 3, 4, 5. The parent of E must be 3 by 2 is 5 by 2 is how much? 3, right? So
It
5 by 2 is 2.
It should be 2 because the floor function.
Right. And 2 is 1, 2 for B. We good. Parent of E is B. Right.
So what we've done here is given this array structure a higher connectivity, right?
We have given them a connectivity in some sense.
Yeah.
I mean, I can now think of an array as a heap and a heap as an array. Or not
Okay.
heap, I will not say heap here. I can think of an array as a complete bipartite graph, a complete binary tree, and a complete binary tree, I can think of it as a array. Right? And very easy
Right.
to do. Sorry, not complete binary, balanced binary tree is nothing but an array. That's it. You can view a balanced binary tree as an array. You can think of an array as a balanced binary tree. The data are stored. Okay, orderings are different, by the way. If you say, okay, what's the previous element in an array, that might be F's previous element can be E. But what is the previous element of an E, F, or parent of F in a balanced binary tree that is stored in this array? That would be D.
So you're saying that if we ask a binary tree, what is the previous element? From the third element, it can't go to the second element. It only has access to the parent, not to the siblings.
No, not
Okay.
to siblings.
Unless we bind these two data structures together in this dual form that you've mentioned.
I mean, so if I think of a binary tree as an array, I'm not going to ask you how to go to a sibling. Or if I think of a array as a binary tree, I'm not even asking about what is the sibling of it. There's no question about that.
Right.
In a binary tree, I'm only asking what's this parent, what is left child, what is right child. That's it.
Right. Okay.
That's it. Okay. Yeah. Perfect. Now, I'm not even defined what is an array heap is. Okay. But so heap is a balanced binary tree such that, okay, the data, so of course, so this every okay, so first that, okay, so maybe every node contains a data, okay, a value, an object, and number two, maybe let's call this one data, maybe call the value, contains a value. So if the node is I, then let's call this one V of I, is the value that is stored in that I. And if J is a descendant, or just forget descendant, J is a child, okay? J is a child of I, then the value contained in J must be bigger than or equal to the value contained in I. So these are the only two properties that I want to maintain. So let's see, let me give you an example. Okay. So here is something that I can think of. Okay. Maybe this is 1, this can be 6, can be 3, 7. Just one second. Yeah, sorry. 10, 3, sorry. This 8, 7, 9, 4. So this is a heap. Okay. So the best way of seeing is that, okay, that if you take any subtree, okay, any node, so this node contains the value that is more than its child. Of course, this value is more than this child. This value is less than more this child. This value less than this child, which means that any node contains a value that is the minimum among this whole subtree below it. Similarly, 3 is minimum of the whole subtree below it. But I have not put any restriction between siblings. And so, in fact, there is no restrictions here. This cannot say that also this is a depth, higher depth, therefore this has a weight value more than this. No, that's not the case. Look at this. And it can be opposite also. Right. So is the definition of heap fine?
Yes, sir.
Yes,
Okay.
sir.
It's just a way of storing the data such that these properties are satisfied. It seems that this is something very weird set of properties. Okay, it turns out that is not. Okay, so what happens if you look at it in the in the world of array? The array will be pretty bizarre looking. It is far from being sorted. Here it will be 1, 6, 3, 7, 10, 9, 4, 7, 8, 11, and so on. If you just think of it as an array, it is no way looks like a sorted array. It's a bizarre array, right? But still, this structure is something very magical. Let's see. Okay. Say, first of all, okay, can you tell me where is the minimum?
So the first pair.
Topmost one.
Yeah.
Topmost must be the minimum, right? So the root has the minimum. First of all, remember that I had given you three problems, right? One of them, the third one was, can you identify the minimum? Right? And this is something that we can do here. Just in one step, I can say that where is the minimum? Excellent. Now, what about insertion? Can I do an insertion? So let me erase this part or at least move it around. Say I want to insert a value, say 4. I want to insert a value 4. Okay, so I want to do, so this is the heap, I want to insert 4. How will I do it? So first of all, if I insert, so the number of data will increase. Number of data points will increase by 1. Correct? So the balance subtree structure will increase. And we know where the balance subtree structure has to be, right? It has to be here. There's no question. What value we put it is something different. It has to be here. Okay. So let's start with putting a 4 over here. Okay. Correct.
Yes, sir.
But now, let's see what is happening. What is happening is that this 4 violates some problem. It's no longer a heap structure. Because this 4 is not bigger than this 10. Right? So that means this object is not bigger than its parent. So what we can do now is that we can say that, okay, then why don't we swap them? I will bring this 4 over here and 10 over here and just swap this 2. Okay. Now, this of course have no problem over here because 4 was bigger than 10, smaller than 10. So there is no contradiction now here. But can there be a contradiction here?
No, sir.
No. Why not?
Sir, because
Because
we
10 was less than 11, of course. Since
10 was already less than 11.
yes, sir.
10 was already less than 11, right?
yes,
And
sir.
4 was less than 10. So 4 has gone up. So once it goes up, there is no contradiction over here, no problem over here. Right? 4 is therefore smaller than both the left child and the right child. The problem might have gone down to here. Right? So what do we do next?
Swap 6 and 4.
Swap 6 and 4. And let's see what happens there. So there's 6 here, 4 here. Once again, there is no problem over here. Right? Because I've swapped it just now. But can there be a problem over here?
No, sir. Similar argument.
Similar argument. So as soon as it goes up, there is no problem over here. Right? Because 6 was less than 7. So 4 was less than 6. That's why we swap. So 4 goes up. So 4 must be less than 7 also. Okay? And now I come here and I see that, oh, okay, there is no other problem. So, game over. So do you see the algorithm that we have done?
Yes, sir.
So it's like bubble
It's
sort.
a bubbling. Exactly.
Right.
So for insertion, what we've done is that we have added a node at the appropriate place. The appropriate place. The place. Put X. Also, this is about insert X, right? X in the right place. In the not right there. In the new node. And bubble up, bubble the X upwards until a heap is formed. Okay.
Sir, what was the point of making this tree a balanced one?
Tell me what was the point? You guys should be able to answer it. Tell me. We just now had a discussion on
If they're
that.
not balanced, then we could have added this new node. I mean, at any place in the last layer.
Sir, perhaps making.
The observation would not have happened. You could not have stored this thing nicely in an array. If it is not balanced, then you cannot say the left child of I is 2i5. Right?
Sir, could you please show us an example where the tree is not balanced?
Here. So this is 1, 2, 3, 4, 5.
No, sir. What I'm saying is that up
Insertion can be done.
the dth layer.
I can understand insertion can be there.
Sir, I mean up to the dth layer maybe. So suppose
Yeah.
there are d many layers.
Yeah.
Up to the d minus 1th layer, we have the complete tree.
Okay.
And after that, I mean the last layer, that maybe is something something random.
4, 5.
Yes, sir.
What is the left node of 3?
The left node of 3.
Left
is five.
child of 3.
5.
It is 5 here, but how will you know that? How will you know that whether this is the left child of 5?
Okay.
or this is the right child of 5.
Right, sir. Right.
We are only doing this just to store them in an array.
Right. And that's very important. Because at the end of the day, you have to store it, right? You have to store it in an array in a very nice way. If there are other ways of doing it by putting pointers and all. But if you do a pointer, then that swapping things and all doesn't go through. Okay. Because you can store it, you can just flip. When I just written here, right? I just swapped. It's very easy to do it because you know what is an parent of 6. Okay, I know what is the parent of 6, right? Else, I would have to keep a lot of information on what is the parent of this node, what is the child of this node, what is the child of that node. And if I add something or delete something, I will have to update those pointers. Here, I don't have to do any of that. Is this clear? Somewhat, at least.
Yes, sir.
Yes, sir.
Okay, good. Okay, now let's see what happens in the case if I remove something. What will you do? Let's see. If I delete something, what will you do? Okay, by the way, I'm not giving you the formal proof of this, okay? You go and read either any book that you have to understand how to write the pseudocode for this and also the correct proof of it. My job is to kind of give you the intuition of the whole thing. Okay, I'm expecting you that after reading this, you will be able to go back and read and understand what all things are happening in it. So, his structure. Okay. So what happens if I say that, okay, delete, say X, and say X is say this one. What happens if I want to delete this thing? I delete it. Then how can I fix it now?
Sir.
Yeah.
Sir, by deleting are you giving me a number to be deleted? Or
No,
like
are
you giving me an index to be deleted? Like
I am deleting an index to be deleted, sir. I mean, in fact, most of the time I'll just delete the top one. That's it.
Because searching, sir, what if we
searching is very costly here.
Costly, right?
Because yes, searching is very costly here. I'm not asking you to go and find out and then delete.
Okay, sir.
I'm just telling you delete the ith node.
Yes, okay, sir.
Okay. So I've deleted. Then what will I do? Once again, once I delete this, of course the tree gets shorter, right? The tree structure gets shorter. So what should be done?
So the right child, the last 10th one needs to get emptied first. So we have to empty it.
I have to empty. This one has to be done, right?
Yes, sir.
Okay, I have done this one. Okay. So maybe just to follow type of it.
Put 10 on that index, like the blank.
So here 10, right? I have to remove it. But the 10 object, I should not have deleted.
Yeah, we can put it in the root, right?
I can put it in the root. Okay. So maybe I'll use another color here to kind of help you guys see what's happening here. Maybe, okay, I'll put in the root. But now there's a problem. There are this structure thing, right? Like the structure of the root is fine, but there is problem. Like, of course, there is this problem and there is this problem. Now, what should we do?
The swap with a minimum child.
So there I have 2 childs, right? Look at which of them are smaller. Whichever is smaller, so in this case 3, I would swap with them. Now let's see what happens over here. 3, 10. Now thing is that of course this gets have no problem because I have swapped it anyway. There is no violation over here. But can there be violation over here?
No, sir.
No, why not?
Because 3 is the minimum among 3 and 4.
3 was anyway less than 4. I had compared these 2 childs earlier, right? And 3 was minimum. So there's no violation over here. There is no violation over here. The violation has gone down to this side. or this node downward. Again, what do? I look at its two childs. And okay, now what happens? Okay, which of them are minimum? Okay, 4 is minimum. Excellent. So I swap 4 and 10. And by the same logic again, there is no violation over here. And there cannot be a violation over here because again, 4 is always was less than 9 to understand it. I mean, because of how we selected it. And so that. Right?
So also there is no hello.
Yeah,
Hello.
go ahead.
So, hello, sir. There is also no violation of the 3 and 4.
There is no violation of 3. So once there is no violation of 3 and 4 also. Because anyways, 4 was below 3, right?
Yes, sir. So 3 is already the minimum.
3 is already the minimum. 3 is already less than 4. So any object is, I mean, if there is no violation here, they cannot, I mean, yeah, I mean, so if there is no violation here, okay, there cannot be a violation later on over here also. Because 3 is always lower than this 2. Okay. Okay, so maybe you guys should go back and think a little bit on this one and read this whole thing up in a book, whatever book, pick up heap. Okay, so I will give you, so the way I have described it just slightly different, but I will tell you all of this thing just now. So I'm not writing down what is it, okay? I mean, in some sense I have to, yeah, you guys will have this video in any case. Right? I'm hoping this video is getting recorded. Okay, so good. Now let's see what we have this given you the algorithm for the insert and delete. Can you tell me how many components did it require in either of them?
So login.
It is just order login, right? Because it is a complete tree or almost complete binary tree, the depth is just login. This depth is login, and I am going to go up either along a path or go down along a path. And so it is just login, order login, and that's it. Okay.
But there are two operations here, right? One is comparison and one is swapping.
Yes, but still there is two login, right?
Yes, sir. Yes.
It's just order login. So this is what happened, right? I have a heap, okay, and I can do insertion in login. I can do deletion in login, and I can do minimum, find minimum in order 1. So actually, in most of the places, how will you find it is that you can do this following thing. They usually combine these two, and that's how it is usually required. Okay, so maybe I should just also write it. So you can do a insert X, okay, and then there is a delete or remove minimum, because you know where is the minimum, and you just want to remove the minimum. So it's basically find the minimum and remove it. And these are the two operations that are usually required. Okay. Now, okay. So how do you do it? Now, can you give me a sorting algorithm? Let's not worry about space for now. What do? I have this whole array to start with, right? A1 to AN. Right? So let's think of X1, X2 and something. Let's start with making a heap H, which is the empty heap. And I keep on inserting for I equals to 1 to N. I keep on inserting. No, sorry, basically, say I update it. H equals to insert Xi in H. So I will just basically produce a new heap over where all the contents are there, right? And so once I'm done with this, okay, so this whole stuff is called what is called heapifying, or sometimes heapify, meaning you want to have the data and storing in a heap. That's it. And now I have to output it, right? Okay, let me get the ith bit, right? Meaning, yeah. So then what do I do is that, okay, for j equals to 1 to n, meaning for n steps, all I do is that h. So you are getting this one new thing, right? So h comma say a j. This is the, so what is, let me write it down. Okay. So let's say aj is the minimum in this heap, and then I do is that h remove minimum from this h. So I said, okay, now I've got it. Now give me the lowest quantity that you have. And I'm done. Okay, lowest quantity is lowest quantity is 1. Excellent. I write 1 here. Now, have you removed that 1 and make and update your heap? You updated that heap. Excellent. Now give me the lowest once again. So what is the lowest now? It's the second lowest. Right? So okay, it's 3. Okay, good, 3. I write down here. Then again, remove it and make a new heap, and so on. And you see that what I managed to do is that I took this whole elements, all the elements, A1 to AN, I put them in a heap, and then one by one remove that heap elements, right? And that helped me to get the sorted list. Okay. Forget the time, runtime, space time, and everything. But for now, just think about this one. Are you convinced that this is going to work?
Yes, sir.
Yes, sir.
Okay. Now let's see what is the time complexity. What do you think is time complexity? So there are n steps here. For each time I'm inserting will take at most log n. So this whole heapify takes how much time? N times log n. Right? In fact, in the books, you can find a heapifying algorithm that can be done in slightly better time. You can do it in order n also, but I'm not going to do it here. But at least how I have described it, you can do it in order n log n. Okay. And here, how much time does it take? Again, there are n things. Every time it's the order 1 step I take here, and order log n steps I take here. So this also is order n log n. So both these parts are order n log n. So the time complexity in the worst case is order n log n. Okay. By the way, what I just now described, you know, this is what is called, because you're storing the mean, it's called a mean heap. You can also define what's called a max heap, where the condition just changes.
Sorry, sir.
You can also consider max heap, but the condition just changes, where the Basically, any node
Okay, so
must
any-
contain more than
Oh, yes.
this child's. Okay, but the thing stored and the root is the maximum. Okay, just to kind of. Now, what about space? Can somebody give a quick idea of how to have this space?
So n, heap of n.
Why n?
So just we need to store the heap.
Right, but can we somehow store the heap here only in this AIs?
Yes, sir. Because by using that property, that child and I by 2 flows.
Right. So what I can do is that so what we will happen now with that? Okay. At any point of time, I have this AIs, right? I start with this A1 to AN, and I have this kind of a thing. Right? This is a pointer. Right now, there is no heap. I first take an I and said, okay, I'm putting it inside a heap. So, okay. So you put this one inside a heap. Now heap is stored in a length 1 array, right?
Yes, sir.
That is here. So next one, I said, okay, now I have to put the next one. This was say maybe x1. Now x2. Put that x2 in this array. Okay, what do I do? Well, okay, keep this x2 outside maybe for now. Who cares about it? Or actually, you don't even worry about it, right? Because it's an insert heap, right? You think of, you can say that, okay, what is happening is that x2 is already in the place where it should be, except that I have to now, oh, sorry, I made a mistake on that. So this heapify, sorry, I made a mistake. So this is not what is called heapify. This is what is called a build heap. This is what is called a build heap. And heapify is, I mean, we kind of removed it and just moved it up and down, right? This whole thing, moving it up and down, this is called heapify. Okay. So just, I mean, when you read it, you will understand this one. It's just 2 names. Yeah. So basically, you heapify these things because at this point, okay, these 2, I mean, this latest one I've added, but this whole thing possibly violates some heap structure. Then what can I do? Okay, heapify this. Now I move it to the next step. Now, okay, now say maybe by now maybe this 2 has changed, swapped changes. Okay, maybe x2 and x1. Then x3. Okay, then what happens? Heapify this. Basically means that think of this one. Where is this structure now? Okay, where is this? This is basically sitting in this last node. Or okay, and that one I'm kind of pushing it, bubbling it up again. Right? And I again I'm done with it. I take it and I move to the next one. And I keep on doing it. See, I'm reusing the whole space somehow by keeping on heapifying this whole structure and putting it in a very clever way. At the end of the day, when I'm done with the first half, I will be having a complete the same array, right? But the values of this array has been kind of moved around x1, xi2, xi3, some kind of stuff. But this whole thing is nothing but now a heap.
Sir, I didn't get this. So, are we doing it like as the elements are entered in the array, or we have that array A and then we are shifting it around?
As the elements are, we have the array, right?
So we have the array. Okay, okay. So
we
can
have
you
the
repeat this
array.
one?
The red line is basically kind of a pointer, says that okay, anything before that red line is a heap structure. Anything after that red line is not yet inserted inside the heap.
I get it. I get it. I get it.
This is a heap. This is a heap. Heap containing 4 elements. This is some initial stuff. Then I say, okay, now take this x5. Excellent. I want to put it there, right? I say, okay, so that means I want to kind of add one more point to the heap thing. Now of course, See, this structure was heap, right? This structure was a heap. This is the latest addition. So latest addition might be violating something. So I heapify it. I bubble it up. So maybe, so there's this one, right? 5. 5's parent is 1, right? And check. No, I need to change it. I might want to, I have to kind of, so 5 is less than 1. So 5 and 1. Okay, now let's see what happens. 5's parent, this one's parent is 2. This one, 1, right? Oh no, but that's no violation. So good. So now this is a proper done. Is this clear? Or should I kind of give you as an example?
It will be better.
Huh?
So it will be better if you give us a small example.
Okay. Okay, so let's start with this one, okay? So say 3, 1, 2, 1 is not a 1, 2, 3, 1, 6, 2, 5, 9, something like that. Okay, let's see. Okay, so this is the array that has been given to us there. Okay, so first, where is my boundary? At this point, I have a heap which has no element, right? The next, I said, okay, I want to insert one. Okay, so what do? I take that line and put it here, and okay, this is my heap. Okay, does it violate? So let's see what happens here. So that means here, if I will maintain a heap below. So at this point, I have a heap 3, right? So, okay, no problem, done. So this is single heap. I can see that there are no violations. Then I move to the next one. So what does this heap look like? This is nothing but heap with a 1 over here, right?
Yes.
But there is a violation, right? So I am to swap it. Okay, so that means I want to swap it. So 1 and 3 I will swap. So 1 and 3. Okay, good. So that is my thing that I'm studying. Excellent. Now again, let's move it here. Next step. Okay, this is 6. Okay, is there a violation?
No, sir.
No, there's no violation. Excellent. So there's no violation. So this is still a heap. Okay, then I add one more. What happens? That means this is nothing but here. Okay, good. So does it have a heap?
No,
There's a
sir.
violation?
Is there
There is a
violation?
violation, right? Okay, so violation is that I have to replace swap 6, 3 and 2. Basically, so where is 2? 2 is in the 4th place, right? Look at its parents. So look at the parent of, so it's in the 4th place, right? 4. 1, 2, 3, 4, right? So its parent must be in the 2nd place. 2nd place is containing 3. So 2 and 3, okay, there's a violation, I have to swap it, okay? So I just swap it with 2 and 3. Okay, so that's the, so basically in this kind of heap structure, basically it means that I'm storing it here, right? Done. Now, next one, I move it. Okay, where is it? Okay, it's a 3 over here. Sorry, no 3, but 5. Okay, again, what is the parent of, so 5 is in the 5th position, right? So parent of 5 is 5 by 2 is 2, right? 2 contains 2, 2 is less than 5. Excellent, no problem, done. Okay, and like this. So basically at any point of time, this half, anything left on this red line is basically a heap. The thing that the right of this line is still not inserted.
Sir, so even after sorting the whole thing, I mean heap sorting the whole thing,
Yes.
so this may not look like a
Sorted
sorted
array, not at all. Not at all.
So, but
Then we will carry on the
for
deletion.
the heap
Then we'll
structure,
carry on the deletion.
okay.
Then we'll carry on the deletion. I'm not telling you how can you do the deletion with house saving space. You think about it.
Sir, could you please repeat? I mean, so the final product that we get is not a sorted array. So
Correct.
if you impose a heap structure on it, then it will be a sorted array, right?
No,
No, it won't be. It won't be.
it won't be.
Yeah. Yes.
Yeah, okay. So that's the fun part of it. I'm storing the heap structure, but that is not a sorted array. But it still has lot of information in it. What we can certainly say, what can we certainly say? We can certainly say that the first element will contain the minimum. Right.
Then we perform a deletion, right? Deletion of these roots.
Then we'll perform the deletion. So maybe if I just end my whole story over here, let's say, just to kind of make your life a bit more simple.
Sir, we can, as we move this red line, which you were moving,
Yeah.
we can just keep track of this. Like we can move it one space left, and we can call that as the heap. Just that. Like we can just keep track of the red line even if we are deleting. So we don't have to, shift anything or something like. Just swapping.
No, you don't have to shift anything. You don't have to shift anything. Let me show you. Okay. So maybe let's think that this one. I'm doing some lot of artwork.
Sir, in the deletion stage,
yeah,
we can have another red line concept where everything before the red line would be sorted.
Everything, yeah, or in this case, it will be easier to say everything after the red line is sorted.
So actually, if we say that everything before the red line is sorted, then what we have to do is in the part after the red line, we just have to bring the last element to the first, like we have to bring it up right after the red line, and then we just have to gravitate it down, which is just reverse bubble it down.
Yeah, yeah. I mean, basically, I think, yeah, it's similar thing that you have said. Okay.
Right.
So let's see. Let's kind of just for the heck of it, let's say this is the kind of the array that is the uploaded here. Okay. Note that this is not yet sorted. You see that this is not in the sorted order. 1, 2, 6, 3, 5 is not a sorted order, but it is a heap order. Okay. Fine.
Yes,
Now I will just put the number 6. Now what do you do? Of course, what you do is that you first start with getting the minimum. Okay, so getting the minimum is 1. Okay, so maybe I will store the 1 over here. I remove the 1. Okay, take this line, push it back, remove 9, put the 9 over here, and put the 1 over here. Okay, now this is of course not sorted. So what have I done? I have removed 9, I have removed one set, and I have removed this 1 and put 9 here. And now we want to swap it, right? Okay, well, how will you do it? Again, the same kind of technique for bubbling down. So in this setting, there is a problem over here, 9 and 2. Excellent. I want to swap this 9 and 2 because I mean there is a problem with 9 and 2 and 6. Out of them, 2 is the minimum. So I should swap 9 and 2, right? How do I know it? Okay, 9 is in the first place. It's 2 of its childs are these 2 and 3. I look at which of them are lower, and I will swap these 2. The 2 and 9. Let me say here. Okay, 2 and 9. Again, at this point, 9 is at the second place. So if 2 childs are 4 and 5, out of 4 and 5, this quantity is 3 and 5. So 3 is the minimum. So I want to swap between 3 and 9. Right? So I will have to swap between 3 and 9 over here. Note that this heap structure that I'm talking about here, this is just for our reference. Okay, we are just dealing with this. That's it. And now game over. Good. Now what is the next step that I do? Okay. Now again, I want to remove this number. I find out the minimum. The minimum is 2. I stored the 2 over here. I remove this stuff for here, one more, and I put this 5 here and the 2 over here. Okay. So what do I do? That means I have remove this 5. I remove the 2 and put the 5 over here. Now again, does it create a violation? Let's say 5 is
sir.
in the first place, right? Its 2 neighbor childs are 3 and 6, right? It is causing a violation because 5 is not less than 3. So out of these 2, I find out which one is lower. 3 is lower. I swap 5 and 3. Right? So basically, what I want to do is that I write 3 and 5. And here also it would mean that I write 3 and 5. And then you'll see that there is no other violation. Excellent. Now, what do I do? Next step. I want to move it. I want to do again, sorry, I want to again remove the minimum. I find the minimum, root 3. Take this one, put it here. Remove 9. Put 3 here, 9 here. Okay. So note that what is happening is that the thing before this line is still remaining as a heap. They are not sorted. They are heap. And these ones here, they are sorted, but sorted in the opposite direction. But that's fine. Okay, it is sorted in some direction.
The first part is not a heap, right? Right now.
It is. What will happen? It's not a heap right now. No, not right now. I mean, I have done this one, right? It's not a heap right now. You're
Yes.
right. So then there is a violation, like 1's 2 childs are 2 and 3, and there's a violation. So I have to find out which of these 2 are smaller. It's 5 is smaller. So I need to improve this and change it to 5 and 9. Right. So this is the sorted.
Sir, the bubbling up of a light element is what you called heapify, right?
Heapify is like bubbling up or bubbling down of these actually. In some sense, both of them.
Okay, so in either direction. So this is also heapify.
Yeah, this is basically heapify that we are doing.
Okay.
Yeah, it depends upon this kind of this nomenclature changes from the book that you are reading in some sense.
Right.
But more or less, that is kind of how the things are. Okay, so are you sure what's you got it for what happening here?
Yes, sir.
Yes, sir.
So see, we have basically used no extra space. Okay, so maybe if I go up completely here, how we started it. Here we have something which has worst case sometimes n log n. Of course, therefore average case sometimes has to be n log n, and there's no extra space. And it's all basically this is the heap sort. And this kind of shows the power of designing beautiful data structures. Okay. Unfortunately enough, as I told you, I will not be able to go too much into data structures in this course. There will be places where I will kind of point you out that, oh, see, I mean, a data structure, if you apply this kind of a data structure here, then you can gain some speed up and so on and so forth. But that's about it. You might have to read it by yourself. But here, what is happening is something, I mean, you can see it. So basically, this is almost like I'm storing, it is almost like this insertion sort, except insertion sort, it was like, okay, this half has to be in a sorted order. But that was such a strong restriction or such a strong problem, right? That we could not do much about it. It was too much of a tight structure. But see, again, useful thing is that here, if I was storing it and I just had in the half time, I just thought, oh, what is the median? What is the halfway? You could have easily given me if it was stored in a sorted order. But if it is stored in a heap, I cannot say such a thing. I cannot give you that information because that information I have not stored. By not storing some useless information in some sense, I have managed to save a lot of time. Okay. So, I mean, wherever you, whichever algorithm you go or do, yeah, I mean, lots and lots of work, I mean, goes into designing of beautiful data structures. Data structures that are kind of very clever in their handling of stuffs. Right? I mean, if I had told you that you can store the data in such a some of non-sorted order, and that can actually help you in getting a sorted order over the whole thing, you would have not believed me possibly. Right? And this is what is being done here. So I think, oh my god, I have already crossed time. Sorry.
Sir,
Yeah.
sir, how do we know that its average runtime is also n log n? Can we show that the best case is also n log n?
Okay. So if the worst case is n log n, right?
Right.
Then the best case cannot be more than n log n, right?
Right. Right.
Now it can be very low. Okay.
Right.
But now question is that the average case is n log n. Okay. Now this is something that I have not told you guys, and I was thinking of giving you as a exercise almost in some sense. You can take it. Just like I kind of did with this comparison of worst case. Yeah. You can actually say the same thing for average. Try to prove it.
So we're using the similar argument.
Using a similar argument.
Right. Right.
Using the tree like argument, right?
Kind of, yeah. Okay. But not only that the worst case runtime has to be bigger than n log n, the average case runtime also has to be bigger than n log n.
So there we were using some sort of pigeonhole principle on the worst
Here
case.
also it's kind of like that. You have to
So
be
it's the
careful.
pigeonhole principle on the
Yeah, I'm
average.
not telling you. Okay.
Right. Okay.
Yeah.
Okay.
Think about it. Okay. So any questions? So there is a tutorial tomorrow. So I will ask the TS to kind of go over some of these stuffs that we have done so far. If you have any particular questions about anything that we have done, please let us know, and we can try to do it. Also, we'll try to put up a set of problems, maybe even an assignment, possibly. I don't know. I have to think about it. This weekend, if I post an assignment, it will be due in another maybe 1 week or 1.5 weeks.
So can you scroll up to that average thing? So we are saying, so we showed that the minimum of the worst case. Oh, okay, sir. So we are talking about the minimum. Okay, sir.
Yeah.
This is fine.
Yeah. Also, we'll be, or if I post a kind of problem set, then you will have a problem set for another. Yeah, I mean that you don't have to solve it. I mean, you don't have to, you solve it, but you don't have to submit it. And the other thing is that I think there is one class next week only. There is no 2 classes because Thursday is some kind of a holiday in ISI.
Sir, the next week is a holiday. I think so.
Next week fully the holiday?
Yes, sir. The academic calendar is written.
Oh, in the academic calendar, they are given fully holiday next week?
Yes, sir.
Okay. Okay. Issue is that if I have so many holidays, I will not be able to do anything interesting. I mean, I'm assuming they're not. Okay, so maybe I should not. So, okay, so they have sent me an academic calendar, is it?
Yes.
So they had sent a tentative one.
Yeah, but I somehow didn't see a holidays written there.
So it was
It is written down. Actually.
Oh, sorry.
Sort of middle.
so it was written in a very
Holidays.
small print, and it was very easy
Yes.
to miss.
Oh, holiday from 11 to 16 and 19. Wonderful. So 11 to 16 is basically in whole of next week, and 19th is the next Tuesday. So we have no classes for the next 1.5 weeks. Okay. Okay, so I think what I will do then, I'm sorry to say that I think I cannot just let it go like this. Okay. I will do is that I will then take the tomorrow's tutorial, which is 7 to 8, right? And I will try to see if I can. I will not be doing too much, but I will do some amount at least tomorrow from 7 to 8, and then yeah, we can end there for at least this first half, because see, we are talking about this sorting, and I don't want to have this sorting continue after this holiday break. So let me just have a class tomorrow for 1 hour evening or tutorial session. Of course, if you have any doubts and all, bring it to me. I'll be happy to answer them. And else I will be, I will take this kind of class, 1 hour class. Also, we will be posting some problem sets and assignments in this weekend, which of course you can submit maybe after this break and all. But yeah, please try to not forget what we have done. Okay, is that fine?
Okay, sir.
Okay.
Thank you, sir.
Okay,
Thank you.
thank you. Okay.
Thank you, sir.